design of reinforced concrete columns. Just to remind you, for any concrete structure, not any, but 90% of the concrete structures, we need to design foundations, footing, like this one. We need to design columns. We need to design beams. We need to design slabs. We already done with the slabs and the beams. Right now, I will talk about design of columns. Columns mean we have reaction. This reaction will make in this column something called axial force or axial compression force. Okay, so our topic today is talking about columns. By the way, we have two main types of column. The first type called short column. The other type called long column. Anybody can tell me what is the difference between short column and long column? What is the difference between short and long columns? So short columns mean short, long columns mean long. So what is the limit for the short? How many feet? 5 feet, 10 feet, 15 feet? So what is the meaning short and long? Perfect. It's a good answer, Oliver. Thank you. But I need a difference between this one and this one in a simple words, not in a mathematical expressions. You are talking about mathematics. You are talking about numbers. But I need to answer this question. What is the meaning? What is the meaning of short and long columns? The only difference between long and the short columns is buckling. If you are considering the effect of buckling, if buckling of the column make big issue, that means this column is a long column. If the buckling effect can be ignored, can be neglected, can be cancelled, it's not a big deal to consider buckling, you are talking about short column. This is the only difference. Then, what is the limit to consider buckling and not considering buckling? What Oliver said. So I cannot say long column with L equal to 100 feet or short column equal L equal 10 feet. I cannot say this. Why? Because sometimes your column is very, very long, but also very, very thick. Sometimes your column is very, very short, 10 feet, but it's very, very thin. So I cannot consider length only. You have to consider something else, which called R. I believe you learned a little bit about R before in engineering mechanics probably, or strength of material. R called radius of gyration. R equals square root of I, moment of inertia, divide area. So please don't think like this. Short columns mean short. Long column mean long. No. Short column mean buckling is not big issue. It's not considered. Long column mean we have a big issue with buckling. Buckling can cause failure of this column. How can I figure buckling is an issue or not? By length only? No. By cross section only? No. Both of them. So we have a column with length L and the cross section. This one is a length. The cross section will be function or will be used as a function of R, radius of gyration, which equal I section moment of inertia divide area. Buckling. Keep it in your mind. The difference between short column and the long column is buckling. Buckling is very low effect, with a very low effect. Long column, or sometimes we call it slender column, buckle easily. I believe short column will be stronger than long column because buckling will make the column weaker. You know, when I was young, I'm trying to break piece of stick. If I have piece of stick like this, and I'm trying to push it from the top to make it broken, the easy way to put my hand or to push this piece of stick at the middle by the other hand. So push this one and push from the top, I can break this stick easily. Why? Because if you push from here, you can make it curve. Once it's become curve, I can push from the top to break it. That's right. This is the effect of buckling. If you have a column can support vertical force, compression. If buckling happened, the column becomes weaker because this force can break this column easily if this deformed shape happened. Okay, so this is the difference between short column and long column. In a simple way, like Oliver said, if you divide the effective length of the column by the least dimension of the cross section, less than or equal 12, this column can be considered short column. So you are talking about length and dimension of the cross section. Both of them, two factors, must be considered if you are talking about short and long column. So probably you have a column with length equal 50 feet, can be considered short. Sometimes you have a column with 20 feet, sometimes considered long, because this is not the only factor. The length is not the only factor. You have to consider what is the dimension of the cross section, both of them. Okay. Failure of the short column is crushing of concrete. Failure in the long column due to buckling. Guys, I talked here about something called effective length. What is the meaning of effective length? Is it the length of the column? Is it the height of the column? No. We have some concept here. We need to consider them. The first one, something called unsupported length, called L ultimate, or I'm sorry, LU, unsupported length. We have this slab at one floor, and we have another slab at the second floor. So what is the unsupported length of this column? Is it center to center, at the center thickness of the slab to the center thickness of the slab? No. From what? The top face to the bottom face. If this slab has drop panel, do you remember the drop panel? So you are talking about the lowest face or the lowest face of the drop panel to the top face of the slab. So unsupported lens is the lens is considered to be equal to the clear distance between slabs. Sometimes you have a beam. So I'm talking about clear distance between the bottom of the beam to the top of the slab. Clear distance between beams, between slabs, anything else. Sometimes, do you remember what is the meaning of this shape? Anybody remember what is the meaning of this shape? I told you this before. Do you remember? Column head. Column head. If you have a column head at the top of the column, the clear distance from the bottom to the top of the slab. So first step, you need to figure out what is the unsupported lens of a column. Then we need to consider something called factor, effective lens factor, K. Effective lens factor, K. Based on what are the conditions of the end of the column. If your column is hinge or pin and the hinge on the other side, K equal 1. If it fixed from one side and free from the other side, K equal 2. Fixed from one side and fixed from the other side, 0.7. I'm sorry, 0.5. Fixed from one side and hinge from the other side, 0.7. So based on the end conditions of the column, I can figure out K. Based on the column and the slabs and the beams, I can figure out the unsupported lens. If you would like to get the effective lens of the column, multiply K times LU. The effective lens factor K times the unsupported lens of the column. This term is very important. Effective lens. So if you would like to divide the effective lens to the least dimension, you know, guys, your column looks like this. So sometimes we have long direction and sometimes we have short direction. So I'm talking about the least dimension of the cross section. So I'm talking about this one. Effective lens divide this one. If this number smaller than 12, you are talking about short column. Greater than 12, you are talking about long column. Any questions so far? Any questions so far? Looks good. If you are talking about ACI criteria or ACI conditions, ACI has different opinion. To consider your column short or long, you have to consider this expression. If KLU divide R smaller than or equal 34 minus 12 M1 divide M2, this column, if this condition happens, this column will be short. Column or buckling will be neglected. M1 and M2 moment on the column. Sometimes we have a moment here, sometimes we have a moment here, because this column is a member in a frame. For example, M1 and M2. If you don't have moment, please forget this term. Then you are talking about KL divide R smaller than or equal 34. If you have moment, please consider this moment. If most of the cases we don't have moment, sometimes we have. What is the meaning of R? R, radius of gyration. According to ACI, you have 3 different ways to figure out what is the value of R. Based on strength of material R, radius of gyration equal square root of I gross divide I gross area. So for example, if you have a column like this, 20 inch times 20 inch, so inertia, the inertia of this cross section will be 20 times 20 to power third divide 12. Area of this cross section 20 times 20. Radius of gyration of this cross section is square root of inertia divide area. I can get it. We have more simplest form. 0.3 times the dimension in the direction stability is being considered for a rectangular column. Probably I will say, according to ACI, radius of gyration equal 0.3 times 20. That's it. Equal 6. That's it. This one is correct. This one is correct. Probably the 2 values will be very close. It's not exactly the same, but very close. If you are talking about circular column with a diameter D, radius of gyration equal 0.25 this diameter. I'm not talking about my equations. I'm not talking about my opinion. I'm talking about what are the provided values for R in ACI. So this one is okay, this one is okay, this one is okay. But remember the third one only for circular column. Okay. So one of you will ask me, but before he is asking, I will ask you first. Okay, I understand this expression KLU divide R smaller than or equal this number. What about this one? What's going on here? You told me, or the slide told me, this one for non-sway frames. This one for sway frames. What you mean by non-sway and sway? Yeah, I know non-sway, sway, right or left. So what is the difference between this one and this one? Do you know? Guys, are you here? I'm not sure if you watched this video before or not. There is a video in Brazil after the earthquake. Yeah, this one. Did you watch this video? Or Mexico? I'm sorry, it's not Brazil.
Subscribe now and press the bell icon.
Can you watch this one? During the earthquake in Mexico, can you watch? The building is swaying left and right due to the effect of earthquake. In this condition, if you would like to consider if your column is long or short in this situation, you have swaying, then you have to consider this expression for sway frames, because you are watching the video. The building is swaying left and right. due to the effect of earthquake. I'm not kidding, it's a real video. If you are considering stability of the building under the normal condition, dead and live load, we are talking about non-sway frames. Did you get it? Thank you. This is another reason, Burak. Yes. Anything that causes lateral swaying of your building. I'm talking in this video about earthquake or wind load or whatever the reason. But the final situation, your building moving right and left for any reason. That means we have a swing. But if your column is stable, if your building is stable, dead load and live load only, dead load and live vertical, that means we don't have sway. So non-sway frame. So sometimes we have the two situations. So right now, I can figure out that we have two types of column. And I know what is the meaning of unsupported length. Unsupported length means something, the length between the top and the bottom from the two elements supporting your column. Slab and slab, that means the top of the slab and the bottom of the other slab. If you have drop panel, so the bottom of the drop panel and the top of this slab. If you have a beam, so at the bottom of the beam, I can figure out the unsupported length. This unsupported length must be multiplied by effective length factor based on what is the condition, what is the end condition of the column. Hinged, hinged, fixed, fixed, fixed free, fixed hinge, whatever the value of K. Based on K and unsupported length and the radius of gyration, I can say buckling is considered, it's long column, or buckling can be neglected, it's a short column. And by the way, ACI can help you to figure out what is the radius of gyration. If you would like to go to the ideal or the detailed or the accurate calculations are equal square root of I gross divided area gross, or just in a second 0.3 times the dimension or 0.25 times the diameter if the column is circular column. Let's start with the short column. Let's start with the short column. So short columns means we don't have issue with buckling. We are good. Buckling is not a big issue. Short column can be in a different three shapes. The first shape called tied column. The second one called spiral column. The third one is composite column. Composite column will be covered in steel design course in the spring next semester. So composite columns means probably we have steel tube with a thickness T, and this steel tube filled with concrete. So the final cross section called composite. We have steel member and we have concrete member. Both of them interact together to form a composite column. Or sometimes we have W shape, I section or H section inside concrete. This shape or this column can be called composite column. Or both of them, we have a steel tube and I section probably, and we have concrete. All of this stuff will be covered in steel design. So I will focus only on tied column and the spiral column. what is the main difference between tight column and the spiral column? Some of you or some of engineers has a wrong background about what is the difference between tight column and the spiral column. Some of them think spiral column means circular column. Tight column means square or rectangular column. No. The difference between tight and the spiral, not the shape of the cross section, but how did you put the stirrups? Can you watch to this photo, please? Your stirrups in this column looks like a square or rectangle. And we have another stirrup. And we have another one. And we have a spacing in between. That means we have separate. Each stirrups, there is no connection between this stirrup and the next one and the next one. Separate. So we can call it tight column. But for a spiral column, we have only one bar. This one bar looks like a spiral. Can you watch? It's one unit. So the only difference between tight column and the spiral column is the shear reinforcement, transverse reinforcement, which is called stirrups. Stirrups here looks like normal. Stirrup, another one. We have a spacing in between, but this one looks like spiral. Any question? So we decided that we are talking about short column. Inside short column, you need to decide, are you talking about tight column or spiral column? Okay. By the way, spiral column is more expensive, more stronger, but more expensive. Anybody know what is the main purpose of these stirrups or this spiral? Why? Why these stirrups or this spiral in a short column? What is the main purpose? Prevent buckling for what? For a column? For the column? Prevent buckling for the column? No. It's preventing buckling, but not for the column. Because if you are talking about column, please, to prevent buckling, you have 3 parameters, 3 factors only. This factor, K, this factor, and this factor. Anybody see these factors depending on reinforcement? Depending on what is the shape of stirrups? No. The first factor, K, depend on the end conditions of the column. And supported lens depend on what is the clear height of this column. R depend on what is the cross-section area, moment of inertia, dimension, diameter. We didn't talk about reinforcement to figure out this column under the effect of buckling or not. So the main purpose of these stirrups to prevent buckling for the longitudinal reinforcement. Guys, we have here vertical reinforcement. These vertical reinforcements are very thin. I know they are inside concrete, but during applying a force, probably, if you have a huge amount of vertical force, can make buckling for this bar. If this bar is alone, without any connection with the other bars, I can expect buckling for this column. I can show you a good photo. It's very important. Buckling. Buckling failure of a bridge column. Okay, let's watch this one. Guys, can we watch this one? Can you see? Due to the huge amount of force, what happened to the shear reinforcement? What happened? Here is the shear reinforcement. Buckling happened. If you have stirrups holding these bars together, we can prevent this type of failure. Okay? Yeah. Why the earthquake? Okay. This is the answer. The earthquake will make lateral force. This lateral force will cause buckling to the column. If your reinforcement is not prevented from buckling, you can expect this type of failure. And also stirrups to prevent or to support shear. If you have earthquake, we have lateral load. Lateral load means shear. Okay? So if you are not talking about earthquake, the normal life, which is dead and alive, your force is a vertical force. So what is the meaning, or what is the main purpose? What is the function of this spiral? To hold vertical reinforcement together, to work as a one unit, to prevent any buckling of these longitudinal bars. So guys, I'm putting this information here. Ties prevent longitudinal bars from buckling after failure of the cover of the concrete. Tied column, I will start with tied column today. It's very simple. According to ACI, we have this expression to figure out what is the design load capacity. Guys, remember, your column has a vertical force here, or a vertical reaction from the beam, or from the slab, or from the building. We have here reaction. This reaction is a force on this column. This reaction can be called P ultimate. And this P ultimate equal 1.2 dead load plus 1.6 life load. To make sure this column is safe, P ultimate must be smaller than or equal phi Pn. Guys, remember, I told you before, if you are talking about this expression alone, this one called nominal capacity. If you multiplied it by phi, which is reduction factor, so the whole term will be called design load capacity. Phi in column, do you remember what is the value of phi in shear and torsion? 0.75. Do you remember? For columns, whatever the type of columns, it's 0.65 according to ACI. So phi is 0.65 for column, for tied column, actually for spiral columns also. Okay, can you talk a little bit about what's going on here. Okay, 0.8 is a number, phi is 0.65, 0.85 f prime c. Do you remember this value? 0.85. Do you remember? If you have a beam, we have neutral axis, we have a stress block here. This value of stress block equal 0.85 f prime c. And this depth is A, and we have here tension. Do you remember this stuff? So this value, 0.85 f prime c, is this expression. Anyway, area gross, the total cross-section area. The total. Area ST, the area of steel reinforcement only. I'm talking about longitudinal, the vertical members. F yield, the yielding strength of steel. Area ST, the area of longitudinal steel. Any questions so far? Any questions so far? Okay, so how can I design a tight column? It's very simple. You need to figure out what is the value of phi, Pn, what is the value of area gross, what is the value of area steel. So I need finally to figure out what is the value of phi Pn. This value must be greater than or equal the ultimate load. We have some requirement. Please, you need to follow. According to ACI. According to ACI. Just a second. I have issue. Okay. Guys, by the way, I have question. It's outside the scope of the course. I have a pen for this touch screen surface. So the size of the battery is 4A. Very, very, very thin battery. I'm trying to look for it in Walmart, but I didn't find them. The all size is 3A, 2A, probably 1A. But this little size, I cannot find it. So any recommendation? Oh, Amazon. Yeah, I have to wait a little bit. Okay. Yeah, I can order it. CVS, Walgreens, probably in the pharmacy. Oh, okay. Thank you. Yeah, probably. Why not? Okay. Thank you, Cody. Thank you, Roberto. Okay. Guys, from the cross section, we have area steel. And we have area concrete. According to ACI, please, area steel divide area concrete must be greater than or equal 1% and smaller than or equal 8%. The maximum reinforcement ratio in the cross section is 8%. Please don't exceed this percentage. according to ACI, because if you exceed it, this equation will not be valid and your column will be considered composite because you have a huge amount of steel reinforcement. At least you have to have 4 longitudinal bars. If your column is a circular column or square or rectangle, at least you have 4 bars in the steel as a steel reinforcement. Minimum 4, because one of you will say, hey, from my calculations, I found the area steel equal 0.11 inch square. 0.11 is considered one number 3 bar. So this column will be reinforced with 1 bar? No. Why? The area steel, the required area steel from calculation is only this number. Okay, I agree with you, but we have minimum number. We have minimum number in any column, in any tied column. Must be 4, whatever the shape, square or rectangle or circular. 4 bars. And also area steel divide area concrete must be greater than or equal 1%. This is the minimum reinforcement. And the maximum reinforcement smaller than or equal 8%. This is the minimum and the maximum. So I'm talking about minimum and the maximum as area, and I'm talking about minimum as a number of bars. Please, we need to follow this recommendation or this requirement. Actually, the minimum number is 6 if you are talking about a spiral column. The minimum dimension of the column, this dimension, you are talking about 8 to 10 inch. 8 inch is okay, 10 inch is okay. So probably in the problems, we can figure out what is the required area concrete. So how can I convert this area concrete to this shape as a rectangle shape? Okay, I'm gonna assume this small dimension 10 or 8. Then I can figure out the second dimension. If you are talking about tied column and you are using number 10 or smaller longitudinal bar, please, the ties or the stirrups must be number 3 or greater. If you are talking about tied column and you are talking about number 10 or larger, then the minimum size of the stirrups must be number 4 or bigger. The spacing between ties, we have 48 times diameter of the tie, or 16 longitudinal bar diameter, or the least lateral column dimension. So we need to figure out the smallest value. Anyway, it's not a big deal for this point. Let's do this example. It's a very simple example. For the short column shown below, we have a short column, 16 times 16 inch. We have how many bars? 8, number 9 bars. F prime C is 4,000. F yield is 60,000 PSI. What is the ultimate axial strength, phi Pn, of this column? Guys, this column is a short column. This column is a tie reinforcement are used. So this column will be considered tied column under short column. We are looking for what is the value of phi Pn. This value equal 0.8 phi 0.85 F prime C area gross minus area steel plus F yield time area steel. The exam is open book, so I don't need to remember. Even after graduation, you have ACI, so you can find this equation inside ACI. So go ahead and try to put these numbers. Phi for column 0.65. Area gross, the total cross-section area, 16 times 16. Area steel, how many bars? 8. What is the area of 1 bar? I need to open my table. You remember your table? For number 9. What is the area of number 9? Number 9 is 1. You are lucky. 1. So 8 bars times 1. So the area still will be 8 inches square. Area gross, 16 times 16. 256 inches square. I am done. So phi Pn equal 0.8 times 0.65, 0.85 times 4,000 times area gross 256 minus 8 plus F yield 60,000 times 8. Your final answer will be in pound. Please divide it to be a number in kips. Here is the design. So the strength, the design strength of this column equal, I can give you a number, 0.85 times 4,000 times 256 minus 8 plus 60,000 times 8. All of them times 0.65 times 0.8. This value will be 688,064. Divide 1,000. It will be 688 kip. So the capacity, the design capacity of this column equal 688 kips. Very simple. Very simple. We have another example. Piece of cake. Piece of cake. For the shown short square tight column, we have a column is short square, because one of you will say, hey, he gave us the 18-inch. What about the other side? The length of the other side, it's a square, so the other one will be 18. The applied axial dead load, the dead load equal 150 kip, and the live load equal to 150. The reactions coming on this column at the dead load 150 and the live load 250. F prime C is given, F yield is given. What is the minimum required size of each longitudinal reinforcement? So we are looking for area steel. By the way, the problem said make sure you are using 8 bars. So area steel is still unknown. Let's start. P ultimate equal 1.2 dead load plus 1.6 live load. So 1.2 times 150 plus 1.6 times 250. So 1.2 times 150, 1.6 times 250. 580. Okay. Guys, remember, for design, P ultimate must be smaller than or equal phi Pn. If you would like to design, I'm gonna assume P ultimate equal phi Pn. So P ultimate, which equal phi Pn, equal 0.8 phi 0.85 F prime C time area gross minus area steel plus F yield time area steel. Let's see. What do you have and what is unknown? This side will be 580 times 1,000 to be in pound. Phi 0.65. F prime C 4,000. Area gross 18 times 18. F yield 60,000. What is the only unknown in this equation? Area steel. Then please convert this area steel to 8 bar. And what is the size? 8 bar. And what is the size? Okay, I can do my calculations. Just a second. .85 times 4,000 plus 60,000 time 0.8 times 0.65 divide 480,000 minus 0.8 times 0.65 times 0.85 times 4,000 times 18 times 18. 4.1 area steel equal 4.1 inch square. I need to convert this area steel, which is 4.1 inch square, to 8 bars. So I will divide it by 8. So the area of 1 bar equal 0.51. Open the table. Which bar, the area of 1 bar looks like 0.51? So which one? This one? No. It's 0.44. This 1.6. So I'm gonna use 8 bar number 7. 8 bar number 7 will give you area steel greater than this one. You are good. So the final answer for this one will be 8 bar number 7 as a steel reinforcement.